In this video, I'll talk about the potential energy of a system of 2-point charges. Okay, so let's say you have 2-point charges Q1 and Q2, and these two charges are separated by a distance x. And our goal is to find out what is the potential energy of this system, the entire system, not due to one, but for the entire system. What is the electric potential? That's what we're going to find it out. Okay, for this one, what we're going to do, we're just going to glue we're going to fix our charge Q1. It's not going to move. We're assuming this one is fixed, and then we move the charge Q2 from xi position, which is the initial position, to some other position. We call that as a final position xf. In doing so, what we're going to do, what's the purpose of moving this charge? First, we're going to find out how much work required to move this charge Q2 from xi position to xf position. From this position xi to xf, we're going to find out the amount of work done in moving the charge Q2 in the presence of this charge Q1. That's our goal, is to find it out. The total amount of work done and moving the charge Q2 from xi position to xf position. Okay. So let's say this is a positive charge. This is a positive charge and this is a positive charge. If these are a positive charges, then the force onto this charge is F12. Recall, what is F12? F12 is a force on the charge 2 due to the charge 1. The force on charge 2 due to the charge 1. And it is away from the charge. Now let's find out the work done. The work done, as we remember, is the formula is the force times dx vector. This is the dot product. So here we're just going to calculate the total amount of work done. And WIF is the work done in moving charge 2 from position I to F, from initial position to final position. And as we're moving from xi to xf, and F12 times dx. And here the force and the displacement are in the same direction. If we move this charge, now let's say I'm not going to do that, but if we move this charge in some other direction, then you have to take the components. Okay, but for simplicity, we're just moving in the direction of the force. Okay, and by Coulomb's law, what is the force acting on this charge? The force acting on the second charge is given by this formula here, K Q1 Q2 over x squared. And what is x here? X is the distance between the two charges at any point or at any moment. So this is the force now, and this is the dx. K, this is a constant term, so we'll just take it out of the integration. Then we are left with dx divided by x squared, because this is the only variable now. If we integrate x squared, what we get? We'll get negative 1 over x. Okay. Then again, the limit is from xi to xf. For those who need the formula is here. X to the n dx is given by x to the n plus 1 divided by n plus 1. So this is how you do the integration. Okay, so once after putting the limits, this is the total work done in moving the charge from initial position to the final position. And the electric field is a conservative field. What does that mean? That means it doesn't matter in which direction you move. the total work done depends only on the initial point and the final point. It doesn't depend on the length of the path. It only depends upon the initial and final position. And for the conservative system, the change in work done or the change in the potential energy is equal to the negative of the work done. Okay, so now we can find out the change in the potential energy of the system, and which is exactly equal to the negative of the work done. So now, so this is again the change in the potential energy, which is the final potential energy minus the initial potential energy. And as this is a negative of the work done, we already have calculated the work done. So this one will be positive and this one will be negative because you have a negative sign here. So what I will get out is exactly the work done, but now with the opposite sign here. This term negative will be positive and this positive term will be negative. Now, let's compare the right hand and the left hand side. So UF, which is the final potential energy, will be exactly equal to this value, and the initial potential energy of the system will be exactly equal to this value. That's what I have written here. This is the final potential energy of the system, and this is the initial potential energy of the system. And what does that mean? That means at any position, the potential energy can be given by this formula. Exactly, K, Q1 and Q2, and X is the location. It can be any location. That's what X means. X is a variable. Or sometimes we also represent it by R. It's the same thing. If we're moving along the x-axis, that's how we write down X. But if we move in any location in 3 dimensions, then we choose to write down R. Both exactly represents the same thing. So this is the potential energy of a system of the 2 charges. Okay, and remember, this potential energy is a scalar quantity.